In this next lesson, we're moving from sampling and analyzing the water to monitoring the flow rate of that water. And that starts with describing weirs. The most common continuous discharge or continuous flow rate measurement method uses what is called a stage-discharge relationship. Stage is a different way to say water depth or water surface level, like I'm showing in the picture. That ruler is helping to estimate the river stage. Flow rates in subsurface drainage or streams or river flows, flow rates themselves are difficult to measure directly. But water depth is not difficult to measure, even continuously. So we develop a stage-discharge relationship so that whatever the water depth is, that water depth can be related to a flow rate. Stage-discharge relationships use either pre-calibrated structures such as flumes or weirs, or are developed on site with a series of stage and discharge measurements. For us doing subsurface drainage monitoring, one of the most common edge-of-field monitoring approaches uses pre-calibrated weirs in a control structure. So what is a weir? You can think of a weir as an obstruction placed in a flow path where the flow rate of water flowing over the weir can be estimated. There are many sizes and shapes and applications of weirs. In fact, you've probably seen a weir before and maybe you didn't realize it. Two weir terms that are used a lot are the crest, which is the point on the weir that water flows over, and the nape, which is the sheet or curtain of water that flows over the weir. There are sharp and broad-crested weirs. Sharp-crested is generally better because it gives a specific sharp point for water to cascade over, which helps prevent the nape from adhering to the crest. There are lots of different weir shapes, and each shape has its own form of a weir equation. We will only be talking about rectangular weirs, V-notch weirs, and a special combination of those two called a compound weir. Okay, so how does a weir actually tell us anything? Well, on its own, it doesn't. Haha, psych! You have to have a stage recording device or a water depth recording device placed upstream of the weir to log the water depth for you. And then you combine that water depth with the appropriate weir equation to come up with a flow rate going over the top of the weir. What does a stage-discharge relationship or equation look like? When a weir is being calibrated, you end up with a graph like this, where the x-axis is water depth above the crest, and the y-axis is flow rate. From the graph, you get an equation that you can use for your field data. There are general forms of weir equations for each given weir geometry. You don't need to memorize these general forms because we use a very specific set of weir equations for tile drainage research. Keep in mind, though, there are lots of different weir equations, and if you make a new weir, you'll need to calibrate that weir to get the right stage-discharge relationship to use. To continuously measure and log stage data behind a weir, I exclusively use pressure transducers that have associated data loggers in them. The pressure transducer itself senses pressure pushing down on it. That pressure includes the weight of the water on top of it and the pressure of the atmosphere on top of it. Some pressure transducers are what we call vented, where the sensor compensates internally for that barometric pressure, the pressure of the atmosphere. But there are slightly cheaper pressure transducers that are not vented, and you can correct those data after the fact by having logged also barometric pressure with a different sensor. An important thing to realize is that your depth sensor will be logging the entire depth of water, in addition to the pressure of the atmosphere. But the flow rate that you're trying to estimate is just the water flowing over the weir. In other words, the depth of water that goes into your weir equation is just the depth flowing over the weir. So you have to calculate the depth of just that water by subtracting the height of the weir from the total logged water depth. The point is that what matters here is the water that's actually flowing over the weir. Now, take a breath because there is a lot of text on this slide. There are many criteria that need to be met to be able to validly use a weir equation to monitor flow rate. You should read the whole list if you're planning to use a weir to monitor flow, but I will highlight some of the biggies. You need the weir to be exactly level because remember you're measuring water depth over that weir, and water will always find a level even if your control structure is crooked or not plumb. The height of the weir from the bottom of the channel to the crest should be at least 2 times the maximum expected head. The approach section should be straight upstream from the weir for a significant distance that's specified in our criteria. The pressure transducer should be placed at a distance from the weir of at least 3 times the maximum expected head on the weir. There should be an air pocket behind the nape. This is pretty important. There are other equations you would use if you're dealing with submerged conditions. And of course, you have to keep the weir and the upstream area of the weir clean. It creates a real monitoring issue if the pressure transducer gets disrupted or is sitting on a bed of sediment. For example, if you think the pressure transducer is here at the bottom of the channel behind the weir and you think that you're recording this water height, but say the pressure transducer is actually sitting on a bed of sediment that you don't know about, and you're actually recording this height of water, then when you subtract the height of the weir in your calculation, your resulting calculated depth of water flowing over the weir would be smaller than what was actually flowing over the weir. That's because these calculations are all relative. It's the total water depth logged minus the weir height, so the exact placement of the sensor behind the weir is critical. See you next time.